All right, so next function, logistic models with differential equations. So logistic growth is something that is only done in BC, right? And in AB, we just talked about the exponential model. Uh, the difference is when describing a population, there often exists an upper limit, right? An upper limit L, past which growth cannot occur. This upper limit L is called the carrying capacity or the limiting capacity. It represents the maximum population Y of t that can be sustained as time increases. Uh, and that could be, because there's food. The world is only going to be able to hold a certain number of people before people start dying of starvation, for example. So a model that depicts this type of growth is called the logistic differential equation. And it looks like this. It is dy dt equals k times y. So this looks familiar, but we have this little added part. And this added part is 1 minus y over L. Okay? Where k and L are positive constants. Now, another way that you might see this logistic growth man, I gotta find the other definition for it. Yeah, here it is. So the other way that you can see this is it might look like this. It is dy dt is equal to k times y. Sorry. I tend to use p a lot because we use population when it comes to this model. And then here it's going to be L minus P, L minus Y, sorry. It's the same thing as this equation right here, right? It's the same thing, except instead of having Y and dividing out an L, right? So instead of dividing out an L, you get the common denominator over here and um, instead of dividing out the L with the Y, you have the L factored out of that denominator. Okay, so the logistic differential equation of this form results in a solution of this form. I'm going to rewrite this B right here as a C because that is going to be our C of the equation. So just like we had a C in this one, because we are technically separating and integrating when we do this, we're going to have a C here. And the reason I like to put a C here is because it's easy to remember the following. So it is going to be lice minus licked. Okay, so lice minus licked. And I am going to put the L right over there. That should be in there. unless it's in this form. If it's in this form, yeah, the L is not supposed to be there. So it's lice minus kit. Let's get rid of that. But do you see the lice? L I C E minus kit. So if you have the logistic differential equation in this form right here, the logistic growth equation form, the actual equation looks like so. Lice minus ict. In either form, L represents the carrying capacity or the upper limit of the logistic growth equation. A logistic growth curve increases the fastest when the curve reaches half of its carrying capacity. So anytime they are going to ask us, when is this growing the fastest? It is always going to be growing the fastest when L is divided by 2. Okay, so that is going to be the when f prime of x is the biggest. So here's an example. The differential equation of the logistic growth model given by the following has this solution. Find the solution to the logistic growth model for the differential equation that looks like this. So don't let this confuse you. These two are the same. The only difference is that we want to make that guy right there a 10. So we need to find the values of L and K in order to figure out this problem. So we need to rewrite it in this form. Okay? And obviously to make that 10 a 1, we're going to divide. We're going to factor out a 10, right? So when you factor out a 10, put equal sign there. So we're going to factor out a 10. And remember, when you factor out a 10, you're dividing both sides by 10. And don't forget to put it on the outside. So when you factor out a 10, you're technically dividing out 10 from each part. So now you have 20y is equal to, why do I keep doing that? Not equal. It is one equation. 20y times 1 minus y over 10. And once you have memorized this equation, and you notice that y is by itself, this is a 1. Now I know what my carrying capacity is, and that's going to be a 10. So L is 10 and K is 20. And once you figure out your L and your K, you do have your general solution. And our general solution, because we have to remember lice minus kit, okay? I'm going to write this out. My general solution is going to look like this. So L is going to be, right, lice minus KT. Because if you don't memorize this general solution, you're going to have to separate and differentiate this equation and integrate, this equation on every single turn. So it is crucial that you do memorize this. So the L is 10, 1 plus C E minus K, so minus 20 T. So right here is my general solution. The question is what is my particular solution? I need an initial condition in order to solve for that. So the initial condition is 1 is equal to 10 over 1 plus CE negative 20 times 0. Well, negative 20 times 0 is 0. E to the 0 is 1. So we're left with 1 equals 10 over 1 plus C. Multiply both sides by 1 plus C. You got 1 plus C equals 10. So C is 9. Well, C is positive 9, right? I know what the equation looks like. I know that K is that, C is 9, L is 10. So the answer has to be B. The number of phytoplankton specimen in a laboratory tank at time t is increasing according to the logistic growth model. Which of the following statements could be true? So in this problem, you have to identify the logistic differential form and the logistic general form, right? So we need the differential form and the general form. So we know that, so which of the following statements could be true? So A, let's look at A. Why does this not work? Why does this not follow the form? Now, this is the general form, and it should look like this, right? Lice minus KT. So it's almost close. I mean, one could be C, so it's not because of the C, but this form right here, K, because the exponent in the denominator is positive. And if it is a logistic growth model and T, as time is increasing, a logistic growth model, K has to be a negative value, or the exponent has to be a negative. So that's not going to be it. B, this one cannot be it because this is not a logistic growth model. This is actually an exponential growth model. And they told us that the bacteria is growing based on a logistic growth model. How about C? So C, they're saying that the second derivative is going to be greater than 0 for any time t is greater than 0. So if the second derivative is greater than 0, that means that the function is going to be concave up everywhere, right? Concave up everywhere. But we just talked about the fact that logistic growth has a carrying capacity. There is a point where there is a point of inflection and this thing changes. So it cannot be concave up for logistic growth. It could have been if it was exponential. So the only possible answer left is going to be D, and we know that it's going to be D because if you, let's undo the separating and integrating of this function, right? So dp dt, just move over the dt, equals 0.035 p times 170, 1780 minus p. And this looks like a logistic growth model, right? I can factor out a 1780 to put it down here and make this a 1 and multiply this by 1780, but everything looks according to the logistic form. All right, multiple choice number 3. The spread of an infectious disease to workers on a large floor of an office building is modeled by this logistic growth model, where T is the number of days represents the number of infected people. The graph of P of T is shown below. What is the number of infected people when the rate at which the disease is spreading the greatest? So anytime they are asking for the rate being the greatest, that is going to be where there is a change in concavity, correct? Remember, when the rate is the greatest, it's when the second derivative is equal to 0, because that would tell us that the first derivative was a max or a min. And in logistic growth models, what's nice is we know that the rate is growing the fastest or when the derivative is changing concavity, that is always going to be happening at half the carrying capacity. And half the carrying capacity is L divided by 2. And from this function that they gave us, I know what the carrying capacity is. It is 800. That's why it's important to memorize this equation. So if I know it's 800 divided by 2, what is the number of infected people when it's the greatest? That's going to be right there, 400. And if you look at the graph, you notice that it starts off with 0, right? It grows very, very fast. Right here is where it's growing the fastest. And then after that, it slows down a little bit. It's increasing, but at a decreasing rate until it infected everyone in the building, which is the carrying capacity. All right, example 4. The rate at which the natural gas is being extracted from an underground reserve at time t satisfies this differential equation, where G is measured in thousands of cubic feet and T is measured in weeks. For what value of G is the extraction rate increasing the fastest? So again, it's the same type of question, except we're not using the general form or the particular form, we're using the differential form. But I still need to know what is L and divide that by 2. Now, according to this form, I need to remember that L is 64. And 64 divided by 2 is 32. And I'm done. All right, last example. Free response question number 1. So a conservative organization releases 30 panthers into a preserve. After 3 years, there are 50 panthers in the preserve. The preserve has a carrying capacity of 150. The growth rate of the panther population, which is depicted by this equation, has the following solution. I like to put the C in there. Well, find L. Well, right off the bat, the preserve has a carrying capacity of 150. So L is equal to 150. Done. Find C. In order to find C, we need to use some pieces of information. So we know what L is. And we want to find C. So we have a piece of information. We know that when time is 0, they introduced 30 panthers. So I'm going to use that to find C. So I'm going to use the general solution here. So 30 equals L is 150 over 1 plus C E to the negative K times 0. So obviously this turns into 0, this turns into 1. So we've got 30 equals 150 over 1 plus C. Multiply both sides by 1 plus C equals 150. So we got 30 plus 30C equals 150. Subtract 30 is 120. Divided by, well, should have just divided by 30. It's okay. Divided by 30 here, and we've got 5. And then subtract 1. So C is going to be equal to 4, no matter which algebra methods you use. All right, part C. Find the exact value of K, but do not write as a decimal. So we found C. We just got to find K. And in order to find K, we're going to use the second piece of information, and that is after 3 years, they said that there were 50 panthers in the preserve. So 50 is equal to the 150. 1 plus c e. Oh, no, we did solve for c, right? That was the whole point of part B. So 1 plus 4e to the negative k times 3. All right, complete this problem algebraically and you will solve for k. K will end up being 1/3 ln of 2, or you can write it as ln of 2 raised to the 1/3, or cube root of 2. Part D, write the actual model. Okay. We know that it's 150, 1 plus, so lice. The C is 4, E minus K and T. So you solve for K and you have T. You plug in your negative 1/3 ln of 2 or ln of 2 1/3 negative. All right, and use the model to find the population after 12 years. That one's easy. You guys can do this. So that's just P of 12, plug that into part D, and then find the limit of the model as T approaches infinity. Well, because we know that this is a logistic model, there's really not much work to do. I know that the limit as T approaches infinity of this function is going to be 150. Even if you actually did the math, right, and plugged it in, you should get 150. All right, that's it for Unit 7. Enjoy.